Hey everyone, it's Justin again. In the last lesson, you created the unit circle. And now, you're going to explore why it's the single most useful tool you'll ever have in your trigonometric toolbox. By the end of this lesson, you should be able to analyze the unit circle quickly to calculate sine, cosine, and tangent values. First, we'll explore how the unit circle relates to trigonometry. Then we'll calculate sine, cosine, and tangent values from triangles in the unit circle and see what connections we can make. After that, we'll practice some examples together. Here's that unit circle we drew in the last lesson. To start, let's focus on the point 30 degrees around the unit circle. Let's remind ourselves of the sine and cosine of 30 degrees. Do you remember your trig values for 30, 45, and 60 degrees? The left-hand technique that we learned can help remind you of those values. The sine of 30 is 1/2, and the cosine of 30 is the square root of 3 over 2. Hey, wait a second. Some of these numbers definitely look familiar. The sine of 30 degrees is the same as the y-coordinate of the point corresponding to 30 degrees on our unit circle. And the cosine is the same as the x-coordinate. That has to be a coincidence, right? Let's check for 45 degrees. Would you look at that? It works here too. The x value of this point is the cosine of 45, and the y value of this point is the sine of 45. Okay, well, they're both the same number here, so let's just check 60 degrees. And it works again. Okay, maybe this isn't a coincidence. Turns out, it's not. This is something we can take as a fact. If an angle of theta in standard position gives us a point of x comma y on the unit circle, then the cosine of theta will be that x value and the sine of theta will be that y value. You can actually think of any point on the unit circle as having coordinates of cosine of theta, comma, sine of theta. It's easy to mix up which trig function is which coordinate, so be careful. You can always remember that cosine comes before sine in the alphabet, just like how x comes before y. So if you forget that cosine is x and sine is y, think alphabetically. It's actually pretty straightforward to prove this using SOHCAHTOA. I know, we've been saying SOHCAHTOA, and you're probably sick of TOA of hearing it by this point, but the fact that it keeps coming up means that it's important. So definitely commit it to memory if you haven't already. The unit circle is centered on the origin. So a coordinate of x comma y means that we went x units away from the center horizontally and y units away from the center vertically. So the horizontal side of this triangle is x units long and the vertical side of this triangle is y units high. Now, remember that the angle we're looking at is the one counterclockwise from the positive x-axis. That's this angle of our triangle. Opposite side from this angle is y. Adjacent side, x. But how do we know what the hypotenuse is? Well, do you remember that trick from the last lesson? Keep an eye on this hypotenuse of this triangle. Are you watching carefully? The hypotenuse is also a radius of the circle, and the unit circle has a radius of 1. It works for more than just the special right triangles. In any right triangle we draw on the unit circle this way, the hypotenuse will be the radius. So it will always be 1. And that's super helpful because anything divided by 1 is itself. So the sine, the opposite over the hypotenuse, is y over 1, which just equals y. That's what we wanted to prove. The sine of the angle is the same as the y-coordinate of the point. Similarly, the cosine, the adjacent over the hypotenuse, is x over 1, just equals x. The cosine of theta is just the x-coordinate. This is a relationship that's important to remember. If an angle of theta in standard position gives us a point x comma y on the unit circle, then the cosine of theta equals x and the sine of theta equals y. You can even use this fact to create a unit circle from scratch without drawing triangles at all. The 30, 45, and 60 degree angles line up with the fingers we use for the left-hand technique. Take a look at the 30 degree angle and remember the general form of square root of something over 2. There are 3 fingers above the folded ring finger, and the number of fingers above corresponds to cosine, which corresponds to x. So the first coordinate at the 30-degree point is the square root of 3 over 2. And there's 1 finger below the folded ring finger. The number of fingers below corresponds to sine, which corresponds to y. So the y coordinate at the 30-degree point is the square root of 1 over 2, or 1/2. Try pausing the video now to fill in the points at 45 degrees and 60 degrees using the left-hand technique. Did you get these coordinates? If you did, awesome job. Keep this trick in your back pocket for all of the trigonometric trials to come. The logical question to ask ourselves next is, what about the tangent? There's only 2 coordinates, an x and a y, and those are both taken already by cosine and sine. Is there room for one more at the unit circle table? Well, let's think about tangent as the ratio of the sides of the triangle, like we did with cosine and sine. The tangent is opposite over adjacent. In this case, the opposite side is y, the adjacent side is x. So that tells us the tangent of theta is the y-coordinate of the point over the x-coordinate of the point. You should remember this too. But if you forget, you can always draw this triangle and rediscover it for yourself. All right, let's try some examples. Here we have a unit circle with points labeled at 30 degrees, 45 degrees, and 60 degrees. What's the sine of 30 degrees? Well, here's the 30-degree angle, and remember, the sine of an angle is the same as the y-coordinate for that point on the unit circle. That's this point here. So the y-coordinate of this point is the answer, 1/2. Huh. Is that everything? Well, this is normally the part where we write out a formula, do some calculations, simplify our answer. Did I miss that part? No? No. I guess it really is that quick when we have the unit circle. Here's our next example. What's the tangent of 60 degrees? Okay, this one does have one extra step. The tangent is y over x. So the tangent of 60 degrees is the y-coordinate of the 60-degree point over its x-coordinate. That gives us the square root of 3 over 2 over 1/2. Remember that a fraction bar just means division, so we can rewrite this compound fraction as the numerator divided by the denominator. Dividing by a fraction is the same thing as multiplying by its reciprocal, so that's the same as the square root of 3 over 2 times 2 over 1. The 2's cancel, which leaves us with just the square root of 3. And that's our answer. The tangent of 60 degrees is equal to the square root of 3. All right? Now it's your turn. Try using what you've learned so far to answer this question. Which of the following could be the value of theta if the cosine of theta equals the square root of 3 over 2? 30 degrees, 45 degrees, or 60 degrees? Pause the video now and see if you can figure this one out. The answer is 30 degrees. The cosine should always be the same value as the x-coordinate of the corresponding point on the unit circle. At 30 degrees, the x-coordinate is the square root of 3 over 2, which matches our given cosine value. Therefore, 30 degrees is the correct angle that gives us a cosine value of the square root 3 over 2. In this lesson, we learned that, for points on the unit circle, cosine corresponds to the x-coordinate, and sine corresponds to the y-coordinate, and tangent is y over x. You may have noticed that we only talked about points in the first quarter of the unit circle, between 0 and 90 degrees, but this trick works around the whole circle. In our next lesson, we'll explore how to extend the trig functions beyond the 0 degree to 60 degree range. See you then!